We're starting Chapter 2 today, and this is officially Vodcast 5. We're doing sections 2.1 through 2.3. So Chapter 2 is about fluid statics. So what we're really talking about is, when we talk about fluid statics, we're talking about fluids as they sit still. Hang on. There we go. So when we're talking about fluids that sit still, we need to discuss the forces that act on a fluid and how we deal with them mathematically for engineering analysis. So to begin, the first thing that we consider for a fluid, if you recall, we had talked a little bit about the fact that we need to deal with fluid as a continuum. And when I say we have to deal with fluid as a continuum, what I mean is we can't look at the entire system. So if you have a pipe full of fluid, you can look at a section of the pipe, or if you have fluid backed up behind a dam, you can look at a section of fluid behind the dam. So whether it's moving, or later when we start, whether it's still, which we're going to talk about today, or moving, which we'll be talking about later, we always are looking at a piece of it. And then we sort of extrapolate that piece to describe the whole. So today we're going to start with that sort of an analysis. And the first thing that we look at is, the first piece of information that we know is that if the fluid is at rest, the shearing stress has to be equal to 0, because especially for a liquid, but for any sort of a fluid, any tau at all will cause a movement. So if we have a shearing stress, the fluid will begin to move or to deform. So the only sort of stress that we're talking about is normal stress. So we're always talking about the type of stress that acts perpendicularly to a face on the fluid. There. So as we continue with that idea, we also know from Newton's second law that the forces in any vector direction, the sum of the forces in any vector direction will equal the mass times the acceleration in that same vector direction. And in the case of a fluid being at rest, the acceleration will be equal to 0. So if we sum forces in any vector direction, they'll have to be equal to 0, or else the fluid will not be at rest. So beginning with this idea of a continuum, the first thing I've done here is draw the coordinate axis system, where x is coming out of the page, and y and z make the plane of the page. So z is our vertical direction here. And I've taken a little rectangle, which is a differential fluid element, meaning that it is small in the infinitesimal sense, and its dimensions would be del x, del y, and del z. And I'm looking at the force on a point directly in the middle of that differential element. So even though it's tiny, we're sort of talking about this continuity theorem where we're taking an infinitesimally small particle of fluid, but we are assigning a shape to it and giving it a differential size and volume. So if we look at the areas of each of the faces, we can see that if I take del y and multiply it by del z, I'll have the area on the front and back of the cube. Del x times del z will give me the sides of the cube, and del y del x will give me the top and the bottom of the cube. And the reason I want to find those faces is because of this idea that I understand that if the fluid is at rest, that the only type of stress that can be acting on it are normal or perpendicular to those faces. So taking that idea into account, I can say then that the sum of the forces in each of the three coordinate directions, x, y, and z, have to be equal to 0. And I can talk about what a force is by recognizing that pressure is equal to force times area, and therefore pressure times area is equal to force. Now, in these equations, I'm using the macroscopic version. I'm looking at, at larger forces, but in the infinitesimal, that's going to be exactly the same. So I can determine the surface forces, del Fs, and take a look at what's going on in the x on that particular face. Well, this is a little bit different. Let's start back here. If I take a look at the del Fy, I know that that's going to be a del P del Y times the volume and so forth. So we have the directions are the same here, and then times the infinitesimal element. Now, the other thing, this is not a mathematical thing at this point. We can derive this mathematically, but we can think about this intuitively. If you have this little cube as a submerged part of a fluid, there's not going to be any change in pressure from side to side, is there? Because if there were, it would move, or something would happen in an unbalanced fashion. Similarly, from front to back, there's not going to be a change in pressure. However, there is a change from the top to the bottom. For any submerged fluid, so I'm going to draw something macroscopic at this point, just to make a point. If we have, for example, a dam, and we have a water surface behind the dam, right? And the triangle at the top just indicates that that is a free surface of the fluid, in this case water. Well, we know that pressure increases as we go downward in the water. So in other words, if you are submerged directly below the water, your pressure, you're going to experience less pressure than if you're submerged at a very deep level. And this is actually the same thing as if you think about the Earth and the atmosphere being so many miles or feet or kilometers or whatever of atmosphere pressing on a person or whatever object, a manometer or whatever, that is the atmospheric pressure. So the atmospheric pressure is actually a function of the height of the column of air acting on an object. That's why at a higher elevation, if we're down here at sea level, then we come up into the Rocky Mountains, for example, and if we're standing up here in Laramie, Wyoming, or some other high elevation place, we actually have 7,000, if we're at Laramie, 7,000 feet less of that column acting on every object. So that's why atmospheric pressure at elevation is higher. So we can measure atmospheric pressure in a lot of different ways, but basically the farther submerged an object is, the more pressure. So that means that we have an unbalanced situation from the top to the bottom of that cube, just like we have an unbalanced situation from when we are near the surface to when we are closer to the bottom of a submerged situation, whether it's water or air. And that is actually, we'll talk about this a little bit more in just a minute, but that's referred to when we're talking about water as the hydrostatic gradient. Okay, and obviously it's going to be a function of the weight of the fluid, the specific weight of the fluid, and it's also going to be a function of the depth of submersion. Right. So continuing on with this idea then, we have, let's see if I've got everything up here the way it needs to be. There we go. So if we have this difference in pressure between the top and the bottom of the cube, we can account for that, and we can develop an equation that's going to give us a resulting force acting on the element. And if you look at this particular force, we're talking about a vector force. So we have a change in the x direction, the y direction, and the z direction, and we can write that in terms of the pressure gradients in each of those directions. Now, if you recall the idea of a gradient is the direction of maximum change. In this case, we're talking about pressure gradients, but in general, a gradient is a vector that represents the direction and magnitude of maximum change. And the mathematical symbol for gradient is del. And sometimes it'll have the parentheses after it, just indicating that it's a function of something else. Well, the important thing to notice here on our drawing is for a hydrostatic gradient, or for a fluid at rest, del is all vertical because it has to do with the weight of the fluid column, whether it's a liquid or a gas. So in this case, del is going to be something for the coordinate systems I drew before. So this is x, y, and z, something in the z direction, which is the k unit vector. All right, and if you consider going through the math, what it turns out for is you get that the summation of forces in the z direction equals 0, and basically then that the gradient of pressure, or the hydrostatic gradient, plus gamma, which is the specific weight of the fluid in the k direction, is equal to 0, because del p del x is equal to 0, and del p del y is equal to 0, and del p del z, turns out, is equal to minus the gradient. So there's two different ways that we can develop it. We can kind of develop it in a more common sense way, or we can go to a more mathematical way. But this is the equation for the hydrostatic gradient. So what this tells us is that if the fluid is incompressible, like most liquids, and also if it has a constant density. This is a point that's not really brought out in your textbook, but there are times where the fluid will not have a constant density. For example, you can have a fluid where heavier elements of it will settle to the bottom, so that at the top of the fluid it may be actually lighter. The gamma value may be less than it is at the bottom. Gamma equals weight per volume. Okay, just to clarify that. So if it's incompressible and constant density, or constant gamma, del p del z equals minus gamma, del p equals minus gamma del z, and if you do the integration from p2 to p0, from z2 to z0, you find that p2 minus p1 is equal to, minus gamma comes out, and you get z2 minus z0, or it's often rewritten so that this is gamma times z0 minus z2. So the only thing that's really important to notice about the sign convention is that as depth increases, well, if you think about this, as depth increases, what happens to z? Z decreases, doesn't it? So z decreases with depth. So the minus sign is really just a function of the coordinate system. So z decreases with depth, and pressure increases with depth. And that's why the minus sign shows up. So if you use it as, and this is often the case when people work with this, they'll just go a deeper depth equals a deeper pressure, and then you sort of use this as a delta, and this goes away. The minus sign goes away. But another way, I guess, to write this would then just be in the final analysis that the pressure at depth is equal to the pressure at the surface, if it's P0, plus gamma times the negative of delta Z, which is Z0 minus Z2. Right? But if the fluid is compressible, it's a little different. For a compressible fluid, that means that gamma is not a constant. And therefore, when you do the, when you go back to the original integral, you cannot pull gamma out of the integral sign. So what that means is that we need to have gamma as a function of Z. Right? Now there's a lot of different ways that that can be written, but you just have to have that function, whatever it is. Now one example is what if, first of all, the thing, most compressible, most liquids, let's put it that way, are considered incompressible, and gases are almost never considered incompressible. So what that means for us is that if we have a gas, we need to have that some sort of a relationship that tells us what gamma is as a function of Z. One example that your textbook gives is if it's an ideal gas. Okay, you remember from chemistry or thermodynamics that the ideal gas law says that P times V is equal to mRT. And if I divide both sides by V, I get an expression that looks like this. We know that mass per volume is density. So I can write the equation like this. All right, now I could also say density, which is mass per volume, and we have gamma, which is weight per volume, and we know that weight is equal to mass times gravity, right, from Newton's second law. So I can write weight as mass times gravity over volume. So I can also say that gamma is equal to density times gravity. Okay. Now, one student had emailed me a question, and I want to show you how the units work with this. So I'm just kind of going to do a side. But basically, if you take this set of dimensions, let's work in the SI system. It turns out to be the same thing in the British gravitational system. But basically, we know that newtons, if we take a mass of a kilogram and we multiply it by a gravitational acceleration in meters per second squared, then we'll get newtons. We further know that for weight, we use a standard gravity, generally speaking, of 9.8 or 9.81 meters per second squared. So what that means for us is if you look at this equation, newtons equal kilogram meter per second squared. If I divide by kilograms, I can also see that a newton per kilogram is dimensionally equivalent to meters per second squared. So what that means is if I can say that gravity is equal to 9.8 meters per second squared, I can also say that gravity is equal to 9.8 newtons per kilogram. And that just makes the conversion a little bit easier, because I can have Newton per kilogram, kilogram per volume, kilograms cancel out, and I just have that gamma equals newtons per volume, newtons per meter squared, or meters to the third in this case. All right, excuse me. So combining these ideas, if I take this equation and I look at this, I think about a pressure gradient, and I say that gamma is equal to minus del P over del Z. And if I look at this and I say then, since this is density, and I know that gamma is equal to density times gravity, so I could then say that gamma divided by gravity is equal to density. And I solve this equation and I say P is equal to gamma over gravity times RT. And then I solve this equation for gamma. I get PG over RT is equal to gamma. All right, now what I have is two equations that are both equal to gamma. So using the transitive property of mathematics, I can set those two equal to each other and write the equation as, can you see everything? Yeah. Negative dP over dz is equal to pg over RT. Yep, there we go. All right, I was just making sure I had all of my terms correct. All right, so in this particular case, I don't necessarily have a gamma as a function of z, but I do have two variables p. So if I rewrote this by dividing through by p, I could say dp over p equals, and I'm going to multiply through by dz, dz times g over RT. And if I integrate both sides from, let's say, P2 to P1 and Z2 to Z1, I then have the natural logarithm of P2 over P1 on the left-hand side. And I can think about what happens here. Well, G is a constant and R is a constant. So then I have inside of my integral dz over t. So maybe I have temperature as a function of z, but what if, in addition to ideal gas law, ideal gas behavior, what if it's also isothermal? That means that my t comes out as well, and I'm just left with z2 minus z1. And I've dropped a minus sign somewhere. I'm going to just move it over here. And so I'll just move it over here. All right, so this equation is the equation, we have to have a fixed temperature. So I'm just going to call it T sub 0, right? But then I could also, you can take e, both sides to the e power, and you get P2 over P1 equals e to this, or you could rewrite it as P2 equals P1 times e, the natural base, raised to this whole thing, minus g times z2 minus z1 over RT0. Okay, so this is one equation for a compressible fluid, but as I said, it's only a certain kind of a compressible fluid. That would be an ideal gas that is also isothermal. Otherwise, you'll have to find a different function and integrate that to get the correct relationship. All right, so that's the end of the material for sections 2.1 through 2.3. I'd like to do a a homework problem for you. Problem 2.8, no, that's my next one. I'm sorry, I got excited. I had 2.84 here. I think I'm going to do 212. All right, and so stay tuned. We'll do 2.84 later, but not not right now. All right, so we'll do 212. So if you look in the back of your text, or at the end of chapter 2, in your textbook, what we see, it's an interesting problem, and there's some really interesting real-world applications for problem 212. All right, and basically what we have is a hydraulic press. And hydraulic press is something that is used in a million different types of applications. One is, for example, if you go to somewhere that changes the oil in your car or works on your car, some of them have hydraulic presses where they will actually raise the car above head so that the mechanic can work on it. Or another one is a simple hydraulic jack, if you're going to jack up your car. You know that your car weighs thousands of pounds. So how is it by pumping on a little handle you are able to raise enough weight? Because you're obviously, otherwise, if you could actually raise that much weight with your hands, you could just stand underneath the car and pick it up, which obviously is not going to work. So a hydraulic press is something that enables you to apply a smaller force and have a resulting larger force by transmitting it through the fluid. And we're going to talk about this a little bit as we work through this problem, but this uses what's called Pascal's principle, which is in a fluid that is continuous like this, a change in the pressure anywhere will result in a corresponding change in the pressure everywhere in the fluid. That's that continuum idea. The fact that everything that happens in the fluid, we can look at one element and extrapolate it in some way to the other elements of the fluid. All right, so 212 reads, the basic elements of hydraulic press are shown. The plunger, which is right here, has an area of 1 square inch, and if we put a force of F1 to apply to it, we are using a lever that has a mechanical advantage of 8-to-1. What that means is, and there's no diagram of what the lever action looks like, but what mechanical advantage is basically using a mechanical device to increase the amount of force that you use through a control system. So in this case, what it's saying is we have a mechanical advantage of 8-to-1, which means that if we push on our lever assembly or pull on a lever assembly or do whatever direction of action there is, with 1 pound of force, we will get a resulting 8 pounds of force acting on the plunger. So in addition to that, we have a larger piston up here, which has an area of 150 square inches. And so what we're asking is, between these two features, the mechanical advantage here and the transmission of pressure through the hydraulic fluid to a larger surface, how much force can we lift at the larger piston based on pushing on the plunger? All right, so if we take a look at that problem and how we solve it, we just use a couple of different ideas. Oops, I'm going to have to telescope this a little bit. There we go. All right, so the problem tells us we have an 8-to-1 mechanical advantage and that we push on the plunger with 30 pounds. So the first thing is the net bang for our buck that we get is 8 times 30, or 240 pounds. We also can say that the force in 1 is going to equal the pressure times the area of 1. That's our 240 pounds. And our force in 2, which is our unknown, is equal to the pressure times the area of 2. According to Pascal, we also know that the pressure is going to be the same everywhere in the fluid. So as long as that fluid is continuous, there's not a baffle or something restricting the flow of that fluid or the motion of that fluid, then this pressure and this pressure are going to be the same. So I can solve both of these equations for pressure, and so I get a proportionality. It looks kind of like a gear ratio, except it's not the same thing, but it's the same type of a proportion where we have a pressure equal to a force over an area, and that same pressure equal to a different force over a different area. So once again, using the transitive property of math, I can set those two equal to each other. the force in 1, or the force in the plunger, as I've subscripted it here, over the area of the plunger is equal to the force in 2 divided by the area of that lift. So if I rearrange, I can solve for F2, and I've written it this way because I want to show you that that is indeed the ratio of the areas multiplied by the applied force, and we get an advantage of 150 times, or we get a force of 36,000 pounds. So I was pushing here with a mere 30 pounds, which is a very humanly capable weight to push with. Using a lever system with an 8-to-1 mechanical advantage, we get 240 pounds, which is quite on the limit of human ability to push something totally out of the realm of human ability by using mechanical advantage and the principle of continuity of fluid. All right, so that's it for sections 2.1 through 2.3, vodcast number 5. There will be a total of 4 vodcasts for chapter 2, so we'll meet again soon for vodcast number 6.